everyone to our current programming language lecture. And today we will talk about a topic which again will be familiar to everyone. We'll talk about different data types, but we'll look in depth and maybe in some challenges. Maybe if you think about something as simple as integer, there are some challenges and different implementation issues in different languages. So we'll look sort of brief overview of the popular data types and maybe what happens when you try to do your own data types. And again, if you got to start from scratch, right? So it's not so simple underneath. Of course, we use them every day, right? We're all very familiar with them, right? So let's take a look. I will open up my usual notebook and we'll see if we can make actually deeper, right? Actually, I had more stuff. Actually, I have two. Okay, so actually, I have open code space. So what primitive data types can you name offhand?
Boolean.
Boolean, okay.
Integer.
Integer, okay.
Char, yeah.
Char? Yeah.
Float.
How about float? Yes. What else?
Double.
Double, yeah. So float and double, yeah. Same group, right? Short, long, right? So there's specifications.
Pointer.
Pointers, of course. Point type variables, of course. Usually, of course, numeric. Which one?
A tuple.
A tuple, yes, that's already, yeah, we'll talk, that's certainly a combination of different values, certainly, so we'll get into components. But which one we are still sort of like forgetting, which most languages include, like the really simple one.
String.
String is kind of difficult actually, but something even much simpler, right? We have something simpler than Boolean.
True.
No, that's true or false. No, but something you are getting there. So who knows? Like almost all languages have this type of specifier. I mean, at least Python has specific, right? At least you need an identifier, right? What do we have? What type do we have? Like the simplest one, which is only single value. Come on.
It's probably
Bit.
so obvious.
I don't know.
Yeah.
Which one?
Bit, I don't know.
Well, you guys know this one. It's sort of like you usually say as a placeholder. Non-type, right? Yeah. So yeah. So it's like sometimes, of course, we need some ID or some identifier for something that doesn't exist, right? Because of course, underneath there's usually a zero or something underneath, but a simple zero by itself is comes with its own challenge. Like a null pointer, of course, usually will be a zero, right? But it doesn't have to be, right? It could be something else underneath. Okay. So you guys know the basics. So you'll see actually have two different notebooks, so there's going to be a deeper dive as well. Okay, that's good. So look at the basics. And so, okay. So data type is basically a classification of data which tells compiler interpreter basically how we're going to use the data. And again, broadly two categories. Primitives, like you already named most of them, right? Derived data types, meaning you derive them from, or maybe you can call them component data types, right? Also, let me add this. Also think of it. Also, we could call not user defined. Of course, is separate category, right? We could maybe derived data types. Well, that's one definition, right? You could say compound, right? We could also classify the derived data types into two categories, right? Let's see what they say. User defined and well absolute data type. That's again, this is maybe not so clear cut. So I would say compound, right? We also have compound, right? Compound or composite, right? Yeah, right. We have So both of the above could be considered as derived data. At least that's my, again, so depending on the book you look at, right, it's different discussions. So, right. So, another definition, a data type defines collection of data values and a set what we can do with them, right? That's another another good definition, right? Meaning what you can do, right? If you define an integer, right? You probably also want to define that you can plus, add things like that, add, subtract, take power and so on, right? That's another thing. So, because again, it would be pretty useless to have an integer which you could not add or subtract, right? For example, right? So that's again, if you're making your own language, it would be, of course, defining it. So let's talk about the primitives. So some of the primitives we know, of course, already, right? So integer, floating point, character. I will add, right? So broadly, right? Very broadly, right? Right? There are many types of integers, right? With sign, sign short, etc. Right? Also similarly, there are different floating numbers, right? Character, right? So character type, right? Not all language implemented. Famously, Python does not have a character type. Good morning. So character type, of course, represents some sort of ASCII value. Well, not necessarily, right? Historically, a single byte, often 2 bytes, or even 4 bytes, right? Depending on encoding, right? I mean, language on type of encoding used, right? For example, UTF-8, right? UTF-8, right? Okay. Now again, historically, again, not true or false. Again, not all languages have a Boolean type. They may use integers, right? So classically, I think original C language did not have Boolean, right? They just used 0, 1. So that's, of course, it's a good underneath, right? Of course, for example, in Python, true or false should also resolve to 1 or 0 underneath, if you think about it. Okay, so also special type, void, right? Void type, right? Or similarly to void, we could have a none type. We have a none type, no value, right? Similar idea actually, right? Void or none, right? Again, undefined, just like also see undefined and null types in JavaScript, right? On other languages, right? So again, there will be difference between what's undefined, right? What's nothing, what's null, right? Undefined and null is not the same thing in JavaScript. Again, like I said, JavaScript is going to get really messy. Again, unfortunately, you will see the JavaScript, at some point in your life, right? So, did we miss anything here? Integers, yeah. So floating point, yeah. Character types. So strings, yeah. So what about strings? They're not technically primitive, right? You can call string. They are basic collection of characters, right? Of singles. So they are compound, really, right? They usually fall into strings. So I'll add a note here that strings are typically, right? Yeah. So why? Because strings are made up of characters, which are primitive data types. So technically, string is a compound data type, right? Technically, right? Of course, it's like, you think that's such a simple thing, but yeah, you have indexing, you have things already that get messy, right? So, all right, so let's go to our numerics. Let's do some numerics. So, right, so again, what's an integer, right? Whole number, right? That can be positive, negative, or 0, right? That's sort of like a very basic definition. Like, think of what you call good morning. So, but if you think about it, integers, right? If you remember your number theory, right? You have, if you go to Wikipedia, numbers, natural numbers, right? right? All different numbers. You have all those big things that we call n, right? I'm just going to just copy since I'm lazy. I wonder if it's going to copy as Unicode, right? So the natural, of course, is for counting from 0, 1, 2, 3. So unsigned, right? Base technically, right? Right. Okay, this is my favorite Shango bone, right? So, right. So think again, but then again, right? So compare integers in computer, in programming with numbers in mathematics. Think, right? Oh no, think natural numbers. Yeah, and so on, right? Why doesn't it copy? I guess this is the one I need to copy. Come on. Yeah, let's copy this one. Natural numbers. Oh no, come on. Oh yeah, actually will work. Okay. Natural numbers, whole real numbers, right? So where's my set of numbers? All of them. Z. What was Z? I forget again. I always forget. Z was everything, right?
Z were whole
Whole.
numbers.
All numbers, right? Numbers. So here we go. N, Z, Q, R, complex C, right? There we go. So integers are Z actually. Integers are Z. Right? Real numbers are real, right? So that's kind of close. So integers, integers, right? Oh, that one kind of converts. How interesting. By some things I can copy paste and some things I can't copy paste. Yeah, N, Z, rational numbers, Q. R. And C. So we get to complex numbers. Have you worked much with complex numbers in any courses?
Not yet.
Not yet. Of course, you're doing electrical engineering, you would have to deal more with complex numbers, right? So, again, so that's a good question, of course, whether complex numbers would be considered, copy image address, right? So image, right? So yeah, the picture here. So we have at least some pictures, numbers, right? So basic stuff, but still nothing is so clear cut, right? So signed integer, right? So again, easy to think about. Yeah, integer is just number. If you're using it right, if you don't think about it, it's easy. But however, as you can see here in Python, integers are really easy because basically that you only have an integer, right? But in most languages, you do have different. Bless you. You do have different different types of integers. Crucially, you have the sign bit, right? Signed or unsigned. And also, crucially, in most languages, what do you have to deal with integers?
Overflow.
Overflow, right, exactly. So in C, if you have only, you have a signed 8-bit integer, what's the highest positive value can you put in a signed 8-bit, sorry, not 8-bit, oh, well, 8-bit integer, it would be a big number. I meant 1-bit integer. I mean, for 8-bit or 1 byte. 1 byte integer, right? It's really short integer, or chart type, right? Signed. Positive number.
2 to 55.
No, if it is unsigned, it'll be 255, right? Unsigned. But if it's signed, what's the highest you can go up? Positive number. So half, but
127.
yes, 127, right? Because, and of course, negative is 1, 20. How much? What's the lowest you can go?
128.
Yes. So that's the interesting thing. Of course, so 0 goes under positives, basically, right? And this holds true for most of the standard implementations. Again, nobody says, you could come up with the idea, I need that extra number for myself on the positive side, right? But historically, that's how it's done. Be good research topic. Why negative values always go down? I mean, because I guess it's just historically because 0-bit was counted as a positive, positive side, right? So obviously most days it doesn't really matter, right? Again, so the storage, the storage issue is is important. Actually, if I think about it, I think the issue is actually if you can go, there's some big tricks you can do in C languages, you know, in low level C. If you go from signed and unsigned, right, using the extra bit, it works better, those bit tricks work better if you keep it as it is. If you went with 128 for positives and minus 127 for negatives, it would not work as well, basically, right? But I mean, you could make it work, right? So, okay, so we go on again, so natural, right, integers, right? So, again, we mentioned before I move on to integers again, so storage, I start talking about, so so Python, so is like I said, is one of the few languages which have this unlimited integer. Again, you have a lot of trouble with overflow. In most languages, you have to deal with special big integer or big num classes, right, which provide this unlimited integer precision, you know, size, right? Again, why? Because, well, machines historically, the standard integer was the size of the architecture, basically, right? You have 16-bit integers, 32-bit integers, right, and 64-bit integers. So they work very well. Like using the default size of addressing works very well. There's for pointer reasons. So once you start going, like you start having something integers which are not the normal size, let's say you have 128-bit or 16-byte integers on a 64-bit machine, like we have 64-bit machine. I mean, it's possible, right? But you know, first of all, there's a big overhead, right? But you need so many, you know, most numbers are not so big, right? 64 bits will give you 18 hextillion, right? You know, or unsigned, it will give you how much? Like half, like 9 hextillion or something like that. Pretty big, still enough. 2 to 63 minus 1, right? So again, integers, right? So complex numbers. So let me do some. Since we have some Python, let's do this again. Code. So let's talk about signed integers, right? Typically, signed integers, yeah. So they go up to, right, and down to -2 and -1, right? So let's see. Let's see some examples using Python, which does not have it, right? So let's bring, let's do so short, some integers, short, bit sizes, right? Bit sizes, we'll do a look, so 8, 16, 32, let's do 128, right? Right. Why not, right? And for bit size in bit sizes, right? Bit sizes. Come on, I'm lazy. Right, so there we go. Min max, right? Ah, let's see the bin hex. That's kind of interesting. Let's see if this happens. Actually, let's see this. This will work nicely. It should. That's more than I want to write, but that looks good actually. Like I said, so yeah, it's actually pretty nice. Thank you AI for saving me like I don't know 5 minutes of typing basically. Right. So binary, right? You can see the binary. What I would like, of course, maybe do a little tab here so we can see the. Be nice to match up basically, right? Maybe I'll do one extra space here, right? Yeah, and this one also. I guess I'll do this. Yeah, I mean max. Right. I like this one here. Let's do this one more time. Yeah. But so let's see, one. Let's see, binary max and binary 3. You see, we don't get the leading 0, fortunately, right? So 3, 6, 7, right? And so yeah, I guess that for binary you need one more. So you can see the offset, right? Yeah. Okay. Right. You can see, of course, so there's 0 here. There's extra 0 here, but you don't see. It's not shown here, right? So easy to see this, right? If you have 8 bits, right? 16 bits, 32 bits, on, right? And you have to scroll for 64 bits, right? You have a huge number, right? I guess I will, right? So you as a scroll, I guess you can do the scroll, right? Yeah. Okay. So 128 bits, right? There's actually 127 bits here, right? Pretty big number. All right, so hex, right? So it works really nicely. You just change a bit, and so easy the math works out when you do the for bit tricks. So the takeaway of this is takeaway. No, mark down. Takeaway from different integer sizes. Right, the 2's complement leads to efficient. Yeah. All right. That's based. So that's the explanation. But again, I would like to do provides idea for to do provide a detailed report on on those complement among different architectures, right? On computer architectures. Yeah, okay. That's of course for another day. Right. So let's go to floating point. Again, nothing too hard, but except actually it is really hard, actually complex floating point. Usage is nice. So we all seen, I think at least I usually show the first day of programming, you show the floating point problems, right? So what happens when you add 0.1 to 0.2 in using floating point? What happens? What kind of result you get? Do you want to see?
0.300 something.
Yeah. Okay, great, good. You remember. Very good. Right. So that is. So we'll talk more about this actually. We can go deeper. So let's do this floating point. Now maybe I'll move this here. No. So simple stuff, right? But right. So that's the problem. This floating point standard is really messy. Really messy. Well, not messy. I mean, it's just if you don't have to worry about it. I mean, thing is, we do have to worry about it, unfortunately, right? Because if you deal with floats, so there are ways around it, but it's that's how everybody does it, right? So let's see this here. Yeah, floating point. Oh yeah. Oh, did I copy twice? Oh, I copied twice. I don't need to copy it. Okay, twice. No, I don't need this one. Python. So everyone knows what happens when you add 0.1 on, right? Right? So, all right, so that's what happens, right? So who knows the reason for this? Which number is the guilty one? All right.
0.1?
Yeah, 0.1 is the problem, right? So because you can try, right? Of course. So reason is, of course, that some numbers don't have exact representation in this floating point standard. 0.1, right, is actually not implemented. Well, you cannot implement precisely, right? So again, I'll show you. I think print. Yeah, hopefully the number is binary, right? Let's see. You can achieve binary. Yes, I wonder. Not in Python. I guess you have to. Oh, let's take a look, right? Oh, that's cool. Right, let's take a look. What the heck are we unpacking here? Okay, all right. I'm not sure. I want to see what's going to happen here. It's trying to do some weird numbers. Let's see. I don't know. Yeah. 2.0, 3.0, 4.0. That's pretty cool. Actually, that's kind of cool. Right. The representation. Right. Structure. Unpack. Right. Pack. Right. Right. Form a string. It's kind of cool actually. Because let's go to Q. Q if I correctly. Let's see. Yeah, rational numbers. Q. You see, there's a reason behind all this madness. Note, right? Q, rational numbers, right? I would guess. I would guess. I would warrant a hypothesis that Q refers to rational numbers, right? Yeah. The keyword Q, right? Right. So, I mean, like a mnemonic, you know, it doesn't annoy. Maybe something else, right? So very cool. But I wonder if I'm doing something from the deeper type. Something we'll do in the second part of this lecture, right? Yeah. Oh, this is a history. This is basic history. This is like a deeper, right? Dive. I will do. This will be characters and list. Okay, yeah, this will be. We'll do later on. All right. So strings that we'll do next in deeper dive. So there's a nice, interesting website. There's a website. All right. Let me see here if I can find it. Representate website for testing. I think it's this one. Let's check. That's one of them. There's a nicer one. If you can find a nicer one, this is okay. So if I type a number, right? So again, this is the standard. This is a worldwide standard, right? So let's do 10, right? So let's do something in float. Let's do. You see, there's a sign bit. That's the easy part, right? And then there's the exponent bit, right? So 1, 2, 3, 4, 5, 6, 7, 8, and then there's mantissa, right? So let's take a look, right? So this is from 2. Let's take a look. So let's say 10. All right, all right. How about 5.2? Okay, no. All right. So 0.2. Okay, actually 0.2 is also not so good, right? So look at the error. So 0.2 is also not great. How about 0.4? How about 0.5? Yes. So 0.5 is preserved exactly. So who knows why? So why is 0.5? So let's see about here. Look at the mantissa. There's no basically, there's nothing, right? So we can see, so 1, 2, 3, 6 bits are set. So basically, I think it shows you, right? The result. 2 to the minus 1. So 0.5, no problem, right? So 0.25, what's going to happen? It's going to be 2 to minus 2, right? So the bits, let's take a look. You see? 2 to the minus 2, right? So it's kind of like reverse, like so. So only thing is what's tricky, right? So the negative value, it's a 0, which says not a 1, like it's like reverse, right? So negative values. So how about 2? How about 2? Right? No, 3 and 3, 2. Right? 2. Right? There's an exponent, right? So 4. No problem. So how about 3? All right. So we still get some mantissa. Is correct? It's still correct. So positive numbers, right? So 2, and we have the mantissa still, right? So that's kind of tricky here, right? Right. So almost all CPUs, right? So base 2, right? So this is 32-bit version. Let's do again. So 0.1, right, is a big problem, right? Right. So hopefully by now, so which one we can 0.5? No problem, right? 2 to the minus 3. Perfect representation, right? So if you need to work with, so what is the takeaway from this? If you need to work with floats and you want precision, you can only do it with powers of 2, negative, you know, divided by 2. And of course, nobody works like that, right? So the mantissa part again and again, you can. There's another visualization. Let me see another visualizer. Maybe this is not bad. There's better one. I've seen a better one. Yeah, another site. Let's check this one. I think this is better one. No, that's also okay, but there is another one which is like nice looking one, right? So that's amount. Yeah. So mine 0.5. Convert, I mean. I want the explanation. Okay. Right. So if I do 0.1, basically we'll just call this is like boring, right? This one is boring. Yeah, I just gives you that. This is not really useful, right? This is not useful, so we'll skip that one. But there's, if you can find, there's somebody made a nice, like nice looking one. I mean, you know, if you're gonna deal with floating point, you might as well look nice. All right. So let me see again. Standard. So standard standard is IEEE 744. On right. Maybe we can go to Wikipedia here as well, right? 1985, right? So, okay. So why did so this is kind of weird, right? I mean, we can't have precise definition because okay. So what's the alternative, right? You saw this. What could we do on some language, including Python, have specific type? If you need the actual precision, how could we do it, right? We could sort of like have a like you would normal people would do it, right? Have a like a floating comma, right? Basically, right? Move it, right? Like say like decimals, right? You know, and have a number basically, you know, to how many shift, you know, how many comma will be shift. But basically, that seems reasonable enough, right? And I think, in fact, historically, some computer architectures use this, right, in some languages. But there's you lose, I mean, you get the precision, right? But you lose the sort of like ability to have arbitrary numbers, basically, right? So like it becomes it's not so simple, basically, right? So arithmetic formats, right? So all standard. There's a house, right? So IBM used hexadecimal floating point power format. That's kind of cool, interesting, right? Let's take a look at this original IBM one, right? So how do they use it? Okay, so longer significant and short exponent, right? So single precision. Oh, I don't want. Oh, my head's gonna hurt now, right? Right. No. Let's make an algorithm, right? Right. So let's do so base, right? Precision, right? Finite numbers, right? Okay, and also what's interesting, the standard defines actually a couple of interesting things. If you read about it, defines of course infinities, useful. You know, if you're dealing with floats, right? You need the plus infinity and negative infinity. Also, but something I have not really encountered myself too much. There are actually two different type of nuns, actually, right? There's a quiet nun and a signaling nun, meaning it mentions there's a meaning to this specific nun. That would be interesting, another topic to see. You see, it's like a rabbit hole. You start dealing with this and you get into deeper into this sort of like a, you know, this topic. But so several numbers might have several possible floating point representations. So you could represent 1, 2, 3, 4, 5. Minus 1 to 2, 3, 4, 5. You can represent with 1 to 3, right? Right. So it does not, of course, matter, right? So, yeah. So for representation, right? So binary, binary, binary. Right. You can see also the precision, right? So again, you see this again. It seems horrible, right? But however, if you think about it, you know this. If you know about this, right? Once you know about it, well, you can deal with rounding, right? What's another issue with this, by the way? What's another takeaway from this, by the way, is that dealing with floats. Where's my book? Where's my notebook now? I went off. I went off too many topics. Oh, there we go. Right. So another thing is, so that's one thing. So it's very careful. Another takeaway is yeah, no. If you are careful, if you are comparing, right? This is like typical sort of bugs, right? Comparing two floats, right? Not necessarily, yeah, right. So what solution you would do? You can do add some rounding, right? For example, solution would be solution for comparing equality, right? Oh yeah, let's take a look at errors. Yeah. Yeah, don't do this, right? So this is, don't do, this is actually, right, edge cases, right? Yeah, right. Yeah. So basically, of course, it depends. Of course, the more this is simplest way, and this usually works. So this guy is really serious about this, right? So yeah, this would be nearly equal, right? Make this a function in C, but you can rewrite it in Python, right? So the edge cases, right? 0.0 divided by 0.0. Let's take a look at this, right? What will happen in Python when both A and Z edge cases in floats? We'll take a break in a moment. So edge cases in floats. Let's take a look at that. So edge cases in float operations, right? So division by 0, right? Print or try. I'll do try because I'll do, of course, try. Print f dividing by 0, right? 0. Right, so what will happen? Of course, there should be arithmetic exception, right? Let's take a look. Yeah, division by 0. Yes, indeed. Okay, but how about now both dividing overflow? I don't think you can get overflow with floats. Let's see what happens. I don't think so. I don't think so. Oh, okay, I guess you can try doing that. That's an interesting one. So 1 to the en, so that is a 300, right? That's a pretty big number, right? Right, that's 300 zeros, right? So 300 zeros, but so this says it's going to overflow. Let's take a look at. So that's going to be how many zeros? 9. Wait, that's going to be 90,000 zeros, right? So I'm going to overflow here 90,000 zeros. Let's take a look. Do you want to break it? Let's break it. No, not 900 zeros. That's not. Yeah, well, yeah, infinity. Okay, we got an overflow. Yes. So not enough room. So not enough room. Paste the result. It would be, so it'd be interesting test to see which one is the lowest number to do. I'll leave it to do. Find out which is the smallest result that will give infinity. Yeah, that's for you guys. Maybe you can give me you just make so underflow. Same thing, of course. It'll be basically the same thing, right? You know, you know. Yeah. Oh, 0.0 actually, because it's very small, right? It's very so. In this case, if you get 0, 0, we got 0. We actually get 0. Yeah, right. So, and I want to now. Oh, none. Yeah, none. I want that one. None. Print none. Yeah. So 0. We are trying to print, right? On, we get none. Right, so it's interesting. Oh, that's very interesting. None, we're trying to print none. Oh, better. So we didn't get none, unfortunately. Right, division by 0. Okay, so the same as before, right? I guess I have to try it. This is a special case. So this is not completely correct for, well, Python just didn't want to make this special case, but 0 divided by 0, it should not be, I think it should not be different, it should be a different type of error, basically, than dividing 1 by 0, right? If you want to be very pedantic, but, yeah. How about 0 by 0? Of course, no problem. How about, so I guess Python does not have this special extra none, right? Is there anything else left? Infinity, we got infinity already. We got infinity. Well, I guess we can do one more time. Yeah. But is this going to be infinity already? No, not yet. Not yet. Alright. So how about, so maybe, is this going to be infinity? Yeah. Again, do what this first number will give you. All right. So So take away from floating numbers, so they are approximations. Again, don't right. There are many edge cases. There are many edge cases. Yeah. So again, but I'm sure it's if you don't remember this lecture, I'm sure real life will teach you that, right? Dealing with floats. So and then you'll bite you. But again, this has been sort of bugs everywhere, right? You know, people thinking floats, you can just compare them without any extra things, and so. Not knowing actually how it, if because in normal usage you don't want to think about how complex it actually is. So let's leave complex. Let's take a short break, like 5 minutes, and then we deal with complex numbers.